I'd first like to express my sincere appreciation to Sofium for giving me this great opportunity. And I have some cough problems, so, but this is not due to coronavirus or influenza virus. I'm negative, but I'm just allergic to certain types of pollen in Japan. Okay. So to start, as Dr. Kubo introduced me, and then I would like to start with oxygen. Molecular oxygen, as you know, is essential for us aerobic organisms. And this is simply because that oxygen is a final acceptor of electrons transferred through electron transport chain to produce ATP in an oxygen-dependent manner. But at the same time, molecular oxygen is a very important substrate for the production of reactive molecular species, such as reactive oxygen species and reactive nitrogen species, such as nitric oxide. As you know, nitric oxide is very important for vasodilation and also certain types of synaptic plasticity in the brain. And we have been very much interested into understanding what the physiological targets of these reactive molecular species. Then we have been interested in trip channels, and trip channels have 28 members, which are divided into 6 families. They have common structural feature like this, as you know very well. And we have been mainly focused on trip M family and trip C family, but occasionally on some other trip channels which show oxygen sensitivity or so on. And according to our work and according to the work from the numerous of the group all in the world, including still sitting right over there, that we know that there are 2 important function aspects of trip channels. One is their calcium permeability, and many trip channels can be considered as non-classical calcium channel. And for instance, such as receptor-activated cation channel or calcium channels, activated by stimulation of metabotropic receptor coupled to PLC activation and downstream signaling molecules. And there is a second important function aspect of trip channel, and that is biosensing function, as you know very well. TRPP1 is probably a champion for the biosensor channel. It's a receptor for the hot compound capsaicin, but at the same time, it's a very important and critical sensor for heat. And for cold sensation, 2 trip channels are responsible. And how about redox sensing? And quite luckily enough, we were the first to identify the real redox-sensitive trip channel, oxidation-sensitive trip channel, that was trip M2. But when we further went into the field, that we found that certain types of trip channels, actually many trip channels, have prominent oxidation sensitivity. But their oxidation sensitivity was completely different from trip M2, and that was oxidative modification of cysteine sulfhydryls, such as nitrosylation by nitric oxide, and hydroxylation, disulfide formation, and so on by reactive oxygen species. And among them are trip C channels, especially trip C5. And as you know very well, trip C is a typical receptor-activated calcium channel, activated by stimulation of receptors coupled to PLC activation and certainly downstream signaling molecules. And in case of trip C5 is very interestingly strongly regulated by extracellular calcium, which permeates through its own channel pore to act from the inside of the channel. And I'll first show you a couple of examples of trip C5 channel responses to nitric oxide and hydrogen peroxide. SNAP and NOR3 nitric oxide donors induce quite robust calcium influx responses only in trip C5 expressing cells. And also, hydrogen peroxide induced a similar robust calcium influx response in trip C5 expressing cells. And in addition to reactive oxygen species and nitrogen species, these compounds called as reactive disulfides are also very powerful activators for trip C5 because they can all electrophilically attack electron lone pairs on cysteine sulfhydryls. And so in wholesale model patch type method, the extracellular application of DTNB, membrane impermeable analog of reactive disulfide, failed to induce any prominent ionic currents through TRPC5. But once this compound is applied from intracellular solution through patch pipette, then it induces very nice current voltage relationship traces characteristic of TRPC5. And also in inside model patch clip method, in the patch excised from TRPC5 expressing cells, another reactive disulfide, 5-nitro-2-PDS, was able to induce very nice unitary currents like this, but this was never observed in vector transfected negative control cells. And also in biotim switch assay, as you can see here, there's a very nice band indicating that wild-type TRPC5 is nitrosylated. But once the mutation was introduced into the cysteine residue localized in the pore structure, it diminished, nearly abolished the nitrosylation pattern of TRPC5 proteins. So according to these results, we concluded that TRPC5 is rather directly modified by reactive disulfides or nitric oxide or nitrosylated, but not these factors such as receptors, G proteins, IP3 receptors are modified or affected by these compounds or this effector in a very low concentration. And we found this in almost, I think it's already 20 years ago, but we haven't studied really what's the physiological significance of our finding. So today I want to show you some results with regard to physiological behavior, what we think physiological behavior and significance of this nitric oxide activated TRPC5 channels. As you know, in vascular endothelial cells, vasodilator stimulation through receptor induces calcium influx and also calcium release to significantly increase intracellular calcium concentration. And this is responsible for the activation of eNOS, as you know, that produces nitric oxide in endothelial cells. So what we first did was to look at localization expression of TRPC5 in bovine arterial endothelial cells. As you can see here in histochemistry data, TRPC5 is very nicely co-localized with eNOS, and these proteins are very much close to each other in the space, because you can see here very nice proximity ligation assay signals with the red dots. And we also looked at co-image precision data and we were able to show that there is actually physical interaction between eNOS and TRPC5 as indicated in this band. And of course, in bovine arterial endothelial cells, a vasodilator ATP receptor stimulation induces very nice nitric oxide production, which is inhibited by eNOS inhibitor alanine. And most importantly, ATP receptor stimulation induced calcium influx activity was significantly suppressed by treatment of siRNA for TRPC5 that inhibits the expression of TRPC5. So TRPC5 is the major player to permeate calcium, to cause calcium influx, and together with calcium release, it regulates the activation of eNOS. And in bovine arterial endothelial cells, as you can clearly see here, that ATP receptor stimulation induces a very robust calcium response like this. But this response, especially at the sustained phase, is inhibited by the treatment of siRNA for eNOS. And the same eNOS siRNA can also inhibit the sustained phase of calcium influx activity upon ATP receptor stimulation, probably mainly mediated by TRPC5. And also in biotin switch assay, TRPC5 protein shows a very nice nitrosylation pattern, as you can see here. And these results can be reproduced also in an recombinant expression system, hexyl system. So when eNOS and GFP, eNOS, GFP, and TRPC5 ds-red are co-expressed in hex cells, you can see a very nice overlap of distribution near the plasma membrane area. And these constructs are interacting with each other very closely, as you can see with this proximity ligation assay data here. And of course, these two constructs for TRPC5 and eNOS show the very nice band in co-image precipitation assay, indicating physical interaction of these two constructs. And most importantly, when TRPC5 was co-expressed with eNOS, calcium influx activity of TRPC5 was significantly enhanced compared to the response in hex cells expressing TRPC5 alone. And there was also a very significant shift of those response curve against ATP to the lower concentration. And this enhancement of TRPC channel activity was only observed in TRPC5, but not in other TRPC homologs. But we can see a little bit of increase in TRPC4 expressing cells, but since the activity of TRPC4 in our system was so low, we were not able to statistically show the effect of eNOS expression toward TRPC4. And in TRPC5 eNOS co-expressing cells, of course, eNOS inhibitor inhibited the calcium influx activity, mainly mediated by TRPC5. And also in multi-switch assay, this nitrosation pattern was only observed when these two components, TRPC5 and eNOS, were co-expressed, but not in hex cells expressing TRPC5 alone. And the results in calcium measurement can be easily reproduced in whole cell model spatial method as shown here. When TRPC5 and eNOS were co-expressed, ATP receptor stimulation is very robust. TRPC5 covered with this IV relationship of traces characteristic of TRPC5. But this was not observed in vector transfected negative control cells. And quite interestingly, when these two components, TRPC5 and eNOS, were co-expressed, upon ATP receptor stimulation, we were able to show a very nice production of nitric oxide indicated by DAF2. But quite interestingly, this was not observed in hex cells expressing eNOS alone. So TRPC5 seemed to be a very important component to induce activation of eNOS. So just to summarize the results up to here, TRPC5 is certainly an essential component for calcium influx, and that in combination with calcium release to activate eNOS. And this is maybe only limited in restricted information for bovine arterial endothelials, but can be also, can be also extended to other systems. Because as you know, that endothelial cells are quite a divergent cell group. And once eNOS is activated, of course, nitric oxide is produced, and this nitrosate TRPC5 protein to activate those TRPC5 that is not yet activated or only weakly activated. And then calcium influx and calcium signaling both are enhanced and amplified, and eventually nitric oxide production is amplified. So definitely there should be a positive feedback loop of nitric oxide production mediated by calcium influx and also TRPC5 activation. And what would be the detailed mechanism of our observation? We were interested in caveolin-1, and caveolin-1, as you know, is a very important regulator for eNOS activation. And it has been reported that caveolin-1 negatively regulates eNOS activity through its direct association. But once vasodilation is applied, then calcium influx occurs, and the calcium elevation leads to the formation of calcium complex, which knocks off this negative regulation of eNOS by caveolin-1 to activate eNOS. So here I can show you that in bovine arterial endothelial cells, TRPC5 is very nicely co-localized with caveolin-1, as you can see here. And certainly the caveolin-1, native caveolin-1 is physically interacting with native TRPC5 as indicated by this very nice precipitation band. And this can be reproduced by a recombinant expression system which expresses TRPC5 together with caveolin-1, which shows a very nice band indicating the physical interaction of these two components. And then we further went in detail in terms of caveolin binding site on TRPC5. In TRPC5, actually, there are three potential caveolin binding sites or known caveolin binding sites. Two are on the N-terminus side, and the other is in the C-terminus side. So when the TRPC5 subfragments was generated for N-terminus, C-terminus, and the transmembrane region, this N-terminus subfragments show a very strong band indicating the binding of caveolin 1 in this region. But on the other hand, there's a very faint band also in the C-terminus which interacts with the caveolin 1. So we thought that this N-terminus, especially the second caveolin binding motif, is the primary binding site, and the C-terminus binding site, the secondary binding site. And just because several groups, especially working on TRPC1 channel, which is quite similar to TRPC4 and TRPC5, demonstrated that two residues in this caveolin binding motif, such as tyrosine and phenylalanine, is critical for the caveolin 1 binding on respective TRPC channel. So, of course, we did introduce mutation in for these two residues. And this double mutant showed lack of interaction with TRPC5 as indicated in this co-precipitation assay. As you can see here, the very good, strong contrast with TRPC5, wild type TRPC5 or different mutant. So clearly, this caveolin 1 binding site is a primary binding site. And when the same double mutation was introduced to the TRPC5 and enos was co-expressed, it really abolished the calcium influx activity of TRPC5 as indicated with this dotted line, and also nearly abolished the interaction of TRPC5 with enos in co-immunosuppression assay. And also in the immunofluorescent data, as you can see here, this double mutant nearly failed to show co-localization in the plasma membrane area with enos in contrast to wild-type TRPC5, which gives a very nice overlap of distribution together with enos, as I explained in the previous slide. And quite interestingly, we also, when we also studied enos mutant, which has no binding ability to caveolin 1, it, of course, showed no lack of binding interaction with caveolin 1 anymore. But at the same time, this mutant also showed lack of interaction with TRPC5. And this mutant, when co-expressed with TRPC5, the enhanced calcium influx activity by enos was nearly abolished. And quite interestingly, in bovine arterial and the in the endothelial cells, siRNA for enos that suppresses the expression of enos was able to significantly suppress calcium influx activity in bovine arterial endocells simulated with ATP-E. And here we also looked at direct interaction of TRPC5 CFE and enos YFE as indicated by this red signal right here upon ATP receptor stimulation. When these two components were co-expressed, there was a very nice initial increase, transient increase of interaction of TRPC5 and enos, which declined and reached to a sustained level. And this can be also examined by using co-immunosuppression assay in the presence of extracellular calcium, that these two components show a very nice band of interaction, but this was nearly abolished when extracellular calcium was omitted. So indicating that extracellular calcium, and probably calcium influx, is very important for the interaction between TRPC5 and enos. And also, we did the GSD polar assay. So when calcium concentration is 100 nanomolar, then the main binding site is in the N-terminal region, as it showed already. But once the calcium concentration was increased, the binding site was shifted from the N-terminus region to the C-terminus region, as indicated with this intense band. So before vasodilator stimulation in endothelial cells, TRPC was very likely to be interacting with caveolin 1, but the interaction between TRPC5 and enos was very likely to be indirect But after vasodilator stimulation, probably due to the formation of calcium carmazine complex, which knocks off Caveolin binding of enos, and enos now shifted toward the C-terminal region of TRPC5 to show direct interaction. And we also looked at plasma membrane localization using TERF imaging for enos GFP and TRPC5 GFP. And TRPC5 GFP alone showed this pattern upon ATP receptor stimulation, showing an increase of plasma membrane localization, followed by a decrease, reaching to the sustained level. But on the other hand, in contrast to TRPC5 GFP, enos GFP showed initial decrease of plasma membrane localization, following by the return back phase of a sustained phase of plasma membrane localization. So the TRPC5 and enos alone, they show very different time independence in terms of ATP receptor stimulation. But if this enos GFP was co-expressed with TRPC5, it showed a kind of similar behavior compared to TRPC5 GFP, indicating that TRPC5 and enos are co-localized and interacting with each other in TRPC5. And this pattern was not observed at all when extracellular calcium concentration was kept low. And to this end, we also looked at rat mesenteric artery system in whole mount preparation. TRPC5 showed very nice localization with enos, like this, and also with Caveolin-1 in endothelial cell layer. And upon acetylcholine stimulation, phenylephrine-induced contraction was significantly suppressed, so there was a vasodilation. And this vasodilation was partially inhibited by TRPC5 selective inhibitor, supporting the importance of TRPC5 in vasodilation of rat mesenteric arteries. So this is a final presentation or summary. Before stimulation, TRPC5 and enos form a ternary complex on Caveolin-1, but they're not interacting directly with each other. But upon receptor stimulation, now of course calcium channel TRPC4/5 is activated to mediate calcium influx. And at the same time, plasma membrane localization of TRPC5 and enhanced probably through translocation from the internal membrane to the plasma membrane. And then eventually, enos is activated, and nitric oxide is produced, and nitric oxide nitrosate TRPC5 proteins to enhance activity and enhance and amplify calcium signals and nitric oxide production. And during this process, most importantly, enos behavior is very dynamic, or I would say the complex is very dynamic, and there is a kind of a remodeling of the complex in which enos is shifting the binding site from the Caveolin-1 to the TRPC5 protein. So I would like to acknowledge my colleague. This work was done in tight collaboration with Dr. Inoue in Fukuoka University and Dr. Shimizu in Teikyo Heisei University. And in my group, the work was done mainly by Dr. Sakaguchi and Dr. Takahashi. And I would like to thank you for your kind attention. Thank you very much.
Thank you, Yasuo, for beautiful presentation. Any questions? Oh, yes.
Hi, thank you for the presentation. I just have a quick question. So you tried to inhibit TRPC5, but did you try to inhibit enos? And do you get the same results when you do that in your previous slide, when you use this? Yeah, here. So when you inhibit TRPC5, you suppress this relaxation of the arteries.
Right.
Yeah. So what happens if you inhibit one of the other complex parts?
Well, of course, that's a very good point, but we haven't tried with the enos inhibitor.
Okay.
But the reason why we didn't use the knockout mice is quite simply because there is a kind of tendency that in case of TRPC channels, even though gene is knocked out, then this knocked out deficiency is very often compensated by other TRPC homologs, and that was one of the reasons. But we haven't really tested with the inos in this case.
So having a knockout of TRPC5, it doesn't just, they survive, the animals survive.
I wouldn't phrase it that way. If TRPC5 or TRPC4 are, which are quite similar, was knocked out, they are quite vital. So that's the reason why we thought that there is a significant compensation, even though the TRPC5 itself is critical in the wild type mice.
Very interesting. Thank you.
Okay, one last question. Oh, yes.
Okay, too bad because I had two, but it's okay. So you said the cysteine which is modified is inside the pore of the channel.
Right, yes.
Is this cysteine also modified by like palmitoylation? Did you check that?
Palmitoylation. No, I haven't tested that.
And would it make like cross-link? Is it in the pore? Can you cross-link this cysteine with the other pore residues?
Well, we haven't done anything like that. So.
Okay. Because so normally the channel is closed, and when the cysteine is oxidized, then
right.
it's open, right?
Right. That is what we have been thinking.
Okay. Thank you.
In this case.
I think there will be some more questions, but please ask questions during the lunchtime. Thank you, Yasuo.
Thank you very much.